Hi guys, welcome back to my channel. First of all, I want to apologize to all of you because I've not been able to be regular with respect to uploading the videos. But here I am, and I'm going to be regular now onwards in uploading videos related to A levels content. Okay, so today's topic that I'm going to hit is logarithms and exponential functions. A lot of students have asked me to help them with this topic, and they have asked me to upload the videos on this. So here's the first video on logarithms and exponential functions. I'm going to keep it short, especially because I want to only focus on what is the content or the concept related to logarithms and exponential functions in this video. In the next two or three videos, we are going to look at purely problem solving. So, if you are okay with the concept of logarithmic and exponential functions, then you might want to move on to the next video directly. Okay, great. So, let's look at the concept of logarithms. Uh, First of all, I'm going to start with a small investigation. The investigation is based on powers of 2. So, we all know that 2 raised to 0 is 1. Similarly, 2 raised to 1 is 2. 2 raised to 2 is 4. 2 raised to 3 is 8. 2 raised to 4 is 16, and so on. Yeah. Now, there was one person who was curious in knowing that as we increased the powers of 2 by 1 unit, the value of the final answer did not increase by 1 unit. In fact, it increased by a different value every time. So, where did this 3 go? Where is this 5, 6, and 7? Where are the rest of the numbers over here? So one guy, he was very interested in understanding that 2 raised to something should give me one of these values, let's say 3. So 2 raised to something should give me a 3. Now to find that something, he had to think about how can I make x the subject in this particular equation. Until now, we have all seen that if we had something like this, life was easy because we could send the power over there and it would automatically become square root, obviously, along with the plus and the minus sign, giving us the value of x. Good thing over here was that the variable was in the base and constant was in the power. So we all probably by now know how to solve variable raised to constant. But this guy, he questioned that what if I have a constant raised to a variable? What if I have that? In such a case, what should I do? Because if let's say I'm working with 2 raised to x equal to 3, and if I try to send the x on the other side, obviously when the power goes on the other side, it becomes the root. So it will become x root of 3, which also doesn't help serve the purpose. Or I'm any which way is not getting the value of x over here. So this would not be the correct approach to find out the value of x. That's the reason he thought, the guy who was interested in all of this, he thought that there has to be a way to work this out. And that is when it struck him that instead of taking the x on the other side, can I rather take the 2 on the other side? And that's when a new function came into picture, and that function was called logarithms. So when you send the 2 on the other side, the new function that comes into picture is logarithms, and you find out log of 3 to the base 2. Now when the 2 goes on the other side, it comes in the base of the logarithm. Yeah, you should know how do we read this. We read this as log of 3 to the base of 2. Log of 3 to the base of 2. Yeah, so good, great. Who this guy was, by the way? This guy was John Napier, if I'm not wrong. One of my teachers, while he was teaching, he introduced logarithms to us this way. And I really loved the way he approached mathematics through history. I'm also trying to do something similar here. Um, so this guy, John Napier, when he questioned as to how do we find out the value of x, he invented logarithms over here. Now, obviously, when we look at logarithm, uh, this, according to mathematics, is an exponential function, or rather, I'm sorry, it should be exponential equation. Should be an exponential equation, right? So then, what would this equation be called? What can I call this equation? It should be called logarithmic logarithmic equation. Yeah. So one thing is to convert from exponent form to log form. Something very basic that we should be able to work out with when we are dealing with logarithms. This is one skill that we all must possess. And what does this say? It says that we should know how to convert from exponent form to log form. So what is exponent form? Exponent form is 2 raised to x equals to 5, let's say. Yeah, this is no doubt an exponential equation, but it is also called that this equation is in the exponent form. If I were to convert this into log form or logarithmic form, how should I do it? I should take the 2 on the other side, and when the 2 goes on the other side, I have the x left over here. It comes from the exponent to the base, and you have log of 5 to the base 2. Now, we should obviously know how to go from exponent to log form. You can take some more examples just so you are a little more clear about this. 3 raised to a is equal to, say, 7. That is the exponent form. I'm going to take the 3 on the other side. A comes down. I have log of 7 to the base 3. Yeah. Similarly, you should also know the vice versa of this. And what is the vice versa of this? The vice versa of this is that you should be able to go from log form to exponent form. For example, let's say I have a log of 10 to the base 3 equals to x. Now that is an equation in the logarithmic form. If I were to go from log form to exponent form, it would look something like this, because I will have to take the 3 on the other side, and that is why when the 3 goes on the other side, it comes in the base and it pushes the x in the power. So now I've gone from log form to exponent form. Exponent form. Similarly, you want to take another example. Let's say you have log of z to the base a equals b. Sometimes when variables are in picture, life looks a little difficult, but that's why I've taken this example. Yeah, the a has to go on the other side. It pushes the b in the power, and that's what you get as your exponent form. Yeah. So now we can say that we are adept with conversion between exponent form and log form. Okay, moving on to the next thing. The next thing is laws and characteristics of logarithm. Laws and characteristics of logarithms. Yeah. Now all these laws have obviously come from somewhere, somewhere that is related to indices. For example, just going through a quick understanding of laws of exponents or laws of indices, as we call them, laws rather, laws of exponents, quick laws, a raised to m times a raised to n makes it a raised to m plus n. Similarly, a raised to m over a raised to n makes it a raised to m minus n. When it is division, the ultimate result is subtraction. When it is multiplication, the ultimate result is addition. And when it is a raised to m, the whole raised to n, it is multiplication. These are the three basic laws of exponents. And we are going to see something similar for laws of logarithm over here. Laws of logarithm. Laws of logarithm will look somewhat like this. First law says that log of a times b. Yeah, log of a times b. It will become log a plus log b. Obviously, I have not written the base over here, which means whatever base you take should be the same throughout. Yeah. If you observe, multiplication is getting converted into addition. Multiplication is comparatively a complex thing to do, whereas addition is comparatively easier thing to do. So log kind of eases our lives. Okay. Similarly, if you had division over here, in case of division, it comes out as log a minus log of b. Obviously, I have not written the base, which means it has to be the same base everywhere. Similarly, the third law is log of a raised to m. This becomes m times log of a. Again, the base has to be same. So here what happens is the power goes into product. See, power goes into product. Division Division over here was also getting converted into subtraction. Multiplication over here was getting converted into addition. Multiplication over here getting converted to addition. Division getting converted to subtraction. Power, which was getting multiplied, is also getting multiplied over here. Yeah. So these are laws that govern, all the algebra that is related to logarithms. Okay. Moving on, some basic characteristics of logarithm we should be aware of. And again, these characteristics, they stem from our understanding of exponents. First thing that I want all of us to reiterate is whenever I say a or anything raised to 1, what is the result? The result is A, or that anything itself. Correct? Now, do you see that this looks more like in the exponent form? Exponent form. Yeah. So, if I were to convert it to log form, my A has to go on the other side, which means this becomes A to the base A. So it is log of A to the base A. Wow, that looks like a basic characteristics of logarithm. And that characteristic is that log of A to the base A becomes 1, which means if you had log of 3 to the base 3, answer should be 1. Log of 10 to the base 10, answer should be 1. Yeah. Similarly, there's another characteristic of indices which says anything raised to 0, your answer is always 1. Correct? Now, if I see this also as exponent form, then if I were to convert this to log form, I would have to send the A on the other side. That will make it look like log of 1 to the base A. Now this definitely looks like it is in the log form. So another characteristic of logarithm is that log of 1 to any base is always 0. Log of 1 to any base is always 0. Yeah. These are a few characteristics of logarithms that we should be kind of aware of. Yeah. Moving on, there is one more idea, and that idea is that let's say if I have 2, yeah, I will raise the 2 to different powers. Let's say 2 raised to 2. I'm getting a positive answer. 2 raised to 10. I'll get a positive answer. 1024, right? Let's say I take a negative power, 2 raised to minus 1. It becomes 1 over 2, which is 0.5. Let's say if I do 2 raised to negative 5, don't you think it will look somewhat like this? 1 upon 2 raised to 5, which is 1 over 32, right? Which will also be 0 point something, yeah? Which will also be a positive number. Now, the idea is that if my base is a positive number, if in a raised to x equals b, if a is positive, then b is also positive. In fact, we can say b can never be negative. B can never be negative, irrespective of whatever values x takes. And when I say whatever values, I will emphasize on the fact that x belongs to real numbers. So, what I'm trying to say in short here is that for any real value x in the power, if the base is a positive number, your answer will always be a positive number. Yes, this also forms one of the bases for one of the characteristics of logarithm, and that characteristic of logarithm is that log of a negative number does not exist. Does not exist. Yeah, actually, it's very deep. At some point in time, We'll try to understand this theory also, you know, out of academic interest, probably. So we'll have to make probably another video on this as to why log of a negative number does not exist. But as of now, prima facie, very basic that you have to understand is that log of a negative number does not exist, and it's beneficial for you to remember this because you will be using this a lot in all your logarithms solving that you will be doing. Okay, so I think we have looked at all the laws of logarithms, we have looked at the basic characteristics of logarithm that are needed for us to be able to, solve any kind of question that is related to your A levels past paper style questions. Yeah. So I'm going to meet with you in the next video where we are going to be full-fledged into solving of logarithmic questions. Yes. So that's it for this video. Thank you so much. Bye bye. See you. Take care.